Okay, welcome to our 1.8 concept video. In this section, we're going to talk about higher order derivatives. Up to this point, we've learned about a bunch of new derivative rules that make taking derivatives a lot simpler. And so now we can tackle functions like polynomials and products of polynomials and rational functions that consist of polynomials because we have these nice simple derivative rules to help us out. And so now we get to explore higher order derivatives. So what does this actually mean? What are higher order derivatives? Well, these really just represent derivatives of derivatives. That's really what higher order derivatives represent. It's me taking an existing derivative and taking the derivative of that derivative. We're taking the derivative of a derivative. Let me show you what I mean by that. And to show you, I'm going to use Leibniz notation. So this will also show you how we notate higher order derivatives. So consider a dependent variable y that is a function of x. So this is my original function. And let's say I want to take a derivative of this. Well, we know how to notate the derivative in function notation. I use that apostrophe. So this is going to represent my first derivative. Notice how now I'm qualifying that as the first derivative because we're going to get to second derivatives and third derivatives. And that's what these higher order derivatives are. But to show this in Leibniz notation, we have to remember this notation right here. D over dx represents taking a derivative in terms of x. So that's what that notation means. So let's use that notation here. And let's take the derivative in terms of x of this dependent variable y. D over dx times y. Well, when I simplify that, I just get dx over dy. And you guys have seen that notation before. When I first introduced Leibniz notation, just that simple dx over dy. Well, let's keep going. Let's find my higher order derivatives by taking the derivative of my existing derivative. So let's take the derivative of the first derivative. Well, to do that in Leibniz notation, I'm going to take the derivative of my derivative. Do we see what I did there? So when I put those two things together, I end up with d squared y over dx squared. So this is my notation for this second order derivative. In function notation, I would just notate that by two apostrophes, f double prime. And this represents my second order derivative or just second derivative. Well, I don't have to stop there. I can keep going. I can then find the derivative of my second derivative. I can take the derivative of that second derivative, which gives me this d cubed y over dx cubed, or f triple prime of x. And this represents my third derivative. So hopefully we're kind of understanding what these higher order derivatives is. It's just taking derivatives of derivatives. And I can keep going with the notation, but it just is going to keep following this pattern. I guess with one exception, once we get to the fourth derivative, that's just so many apostrophes to write that instead we're going to abbreviate it by just putting a 4 up in parentheses up there. And this represents my fourth derivative. We use the parentheses instead of just writing f to the fourth because we don't want to mix this up with f of x being multiplied 4 times. F to the parentheses of 4 is saying that we've taken the derivative 4 times. But from this point, the pattern just stays the same. So dot, 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 dot. If I wanted to keep going, I can keep going as long as I want, right? Fifth derivative, sixth derivative, seventh derivative. As long as my function is differentiable, I can just keep taking the derivative over and over again. But that's my notation. So you'll see both of those types of notation in Pearson. But this begs the question of why is this helpful? Why might it be helpful to find these higher order derivatives? Well, to answer this question, we're going to look at the world of physics. And we've already looked at this to a point, right? And so we're going to continue a very similar conversation that we've already had about what a derivative is and relate that to what a second derivative actually represents. So with physics, remember, a lot of times we will have a position function measuring a position of an object over time. Where is the object after a certain amount of time? And so if we think about, hey, what does the derivative represent? What does s prime of t represent? What is a derivative again? A derivative is an instantaneous rate of change. So what the derivative asks is, how does the position, right? Because s is all about the position of the object. How does the position change over time? Important word there is change, because that's what a derivative is all about. It's a rate of change. And we've already talked about this, but what does this sound like? If I'm measuring how your position is changing, that's really just your velocity, or v of t. So the first derivative is measuring the velocity. How is your position changing? Well, that's speed. Position over time, right? Distance over time, that's velocity. Well, let's keep going. What does the second derivative represent? If I were to take the second derivative of position, what kind of information would that tell me? Well, how did we get that second derivative? We got the second derivative by taking the derivative of the derivative. I want to highlight this right here, right? That's how we got the second derivative. We took the derivative of the derivative. That's what this represents. It's me taking the derivative of the derivative. This isn't the best notation, but this is just me showing that I'm taking the derivative of the derivative. Well, what's the derivative of position? It's velocity. So this is really just the derivative of my velocity function, right? It's the derivative of the derivative, and the derivative is velocity. So it's the derivative of velocity. That means, what question is it asking? It's asking the question, how does the velocity change over time? Right? Similar question, because I'm still taking a derivative. I'm still wondering about a rate of change, but now I'm analyzing the velocity instead of position. How does the velocity change over time? Well, what does this sound like? If you're looking at how the velocity is changing, you might be looking at stuff like speeding up. Are you speeding up? Are you slowing down? What does that sound like? That sounds like acceleration. And a lot of times we abbreviate that just using a of t. So this is where second order derivatives become really helpful, because they can help us analyze acceleration. If I keep going, I have names for them. So like if you go to the third order derivative, the third derivative position is your jerk. And then I think there's names for like the fourth derivative and the fifth derivative, but the farther down you go, the less actually helpful it is to know those things. So in this class, we'll focus on the second derivative. We really won't go past that at all, because the higher the derivatives, the less useful it is. But that's really all there is to 1.8. So go ahead and start the homework, try a few of the problems, and then if you need a little bit of extra help, you can check out the 1.8 examples video, where I'll be going over a couple of the examples from the homework. But I'll see you in that video, and have a great day.